All right, welcome everyone. Today, what we're going to be doing is we're going to be reviewing for exam number 2, which is coming up this Friday from 8 to 10 p.m. Remember, exam 2 is going to be everything we've talked about with sequences and series all the way up until lesson 23, but then we stopped and we're not going to include lesson 24 in there. So I think exam 2, if I'm not mistaken, covers lessons 15 through 23 inclusive. And power series will be on the next exam here. All right, but before we get started with any exam stuff, I have an announcement to make. Now that you guys know about a lot of integration techniques, you may be interested in participating in something called an integration bee. So kind of similar to a spelling bee, an integration bee is where you do increasingly more difficult integrals, and you try to do it within a certain amount of time right here. So it's going to happen this Saturday, March 20th, 12 p.m. over Zoom, and I'll send out the link later. And so there's going to be 2 rounds for this. There's going to be kind of like a general elimination round where you just kind of have like a worksheet of integrals, and then the people who do best on that will go to a single elimination round where you have to do integrals faster than the person that you're pitted against. So it's kind of a fun competition if you like math or integration or anything like that. I think there might be prizes, if I'm not mistaken. I can't remember. There are definitely prizes when I did this in undergrad. So, but yeah, anyways, that's this Saturday if you guys are interested in participating in that. You certainly don't have to, of course. All right. Anyways, let's go ahead and focus on our exam now, which doesn't have too much integration here. So what I want to do first is I want to go over all of the different series tests that we've done, and I want to go over the difference between a sequence and a series. So I want to go over that stuff first, and then I can take questions from all you guys, and on Friday, I'll do more questions from everyone. All right, so first of all, I want to talk about the difference between a sequence and a series, because this is something a lot of people get confused on. All right, so I've already drawn this chart before, but I want to draw it again for emphasis. All right, so there's a different definition for each. A sequence is an infinitely long list, so it's a list of numbers, whereas a series is the sum of a sequence. So it's where we add up all the numbers in the list. So a series is a single number if it converges, and a sequence is just an infinitely long list of numbers. So these are entirely different things, first of all. Second of all, the notation is different. If you see an without a sigma, then this is going to be a sequence. But if you see the sum of an, if you see a sigma right there, you're considering this as a series. And then finally, the last difference between these is testing them. So all you have to do to see if a sequence converges or not is just look at the limit as an goes to infinity. And depending on what that is, whether it's a finite number or it bounces around or it goes off to infinity, that's how you know if a sequence converges or diverges. But a series, if you have a series, there are many different tests for convergence. All you need to do with a sequence is take the limit as n goes to infinity. But with a series, there are many different ways that we can test if it converges or not. Now let's go over all of these different tests here, and let's do it in the order that we encountered them in. The first one was the test for divergence, and this said that if we have a series an, and if the limit as n goes to infinity of an is not 0, then what can we conclude from that? It's going to diverge, right? So then the series diverges. So I think a lot of people understand this. If your sequence diverges, then your series diverges. That kind of makes sense. But even if your sequence goes to a nice number like 1 or 2 or something like that, as a series, that's not going to converge because you're effectively adding up a bunch of copies of numbers that are really close to, say, 1 or 2. So if this limit is anything but 0, your series is going to diverge. Now remember, the thing that this doesn't say is that if your sequence goes to 0, your series converges. And remember, the ultimate counterexample for this is the harmonic series. We know that this is going to diverge. So remember, the reverse reasoning for this is not necessarily true. Just because your sequence goes to 0 does not mean that your series is going to converge. So I want to be very clear about that. This is probably like the #1 mistake made on this exam here. So I want to be clear about that. And I usually don't tell people specific questions on exams. I don't really like to do that, but I guarantee you there will be an opportunity for you to say something converges by the test for divergence. So don't pick that answer. It's a trap. I guarantee you'll see it, and it will be a trap. So don't do that. Okay, so that's the test for divergence. Next, we had geometric series, and we can consider this a test as well. So if we have a series that looks like r raised to the n, and it starts from n equals a and goes to infinity, then one of two things happen. The absolute value of r is less than 1, then the series converges to r to the a over 1 minus r. But if absolute value of r is greater than or equal to 1, then the series diverges. So remember, geometric series are one of the few series that we can actually find the sum of, in addition to knowing if it converges or diverges. And then the other series where we can usually find the sum of it is a telescoping series. And this is where most terms, there we go, cancel with one another. So these two, you can find the sum of. So if we ever ask you to find the sum of a series, it's going to be one of these two series. It's either going to be geometric, where you're going to use this formula here, or it's going to be telescoping, where you write out terms until you see the pattern, and then take the limit as n goes to infinity of whatever formula you write down for that. So these are the two series we can find the sum of, but the rest of them we can usually only see if they converge or diverge, and that's it. All right, the next test we learned about was the integral test. And what this says is that if we have a series an, which has the formula f of n, and we know that f of n is continuous, decreasing, and positive. So remember, we need to satisfy these conditions here. Then the integral and the series do the same thing. So if your integral diverges, then your series will diverge. If your integral converges, then your series converge. And by integral, I mean going from whatever the starting index is to infinity. Like that. So the integral test, honestly, to be entirely honest with you, is not particularly useful on its own. The main reason why we learned about the integral test was that it gave rise to the more useful test called the p-test. Or we also have the generalized p-test. So what are these? Well, the p-test concerns series that look exactly like this. The sum of 1 over n to a power. If p is greater than 1, we have it converging. If p is less than or equal to 1, we have it diverging. So this was the p-test here. And then the generalized p-test is if we decide to throw logs down there too. So in this case, if p is greater than 1, we converge. P is less than 1, we diverge. But if p is equal to 1, then we end up going to q. So it's like a tiebreaker. So if q is greater than 1, we converge. But if q is less than or equal to 1, then we diverge. So q only is going to be impactful if your p is exactly equal to 1. So we can use the generalized p-test if there's only an ln in the denominator. That's right. And in that case, your p would be 0. So 1 over natural log of n is the same as the series for 1 over n to the 0 natural log of n, in which case your 0 would be less than 1, so you would diverge there. So yes, the generalized p-test does that. Well, if it's -1 in the numerator, well, that will turn into 1 in the denominator. What's an example of a function where you can't use the p-test? Something you might be tempted to use the p-test on, but it won't quite work, might be something like this. N squared, 1 over n squared plus n plus 1. So this is tempting to use the p-test because we know that the n squared is going to dominate the behavior of that bottom, but we can't actually use the p-test because this isn't just 1 over n to a power. This is 1 over n to a power plus other stuff. So that's not going to work for the p-test, but we had the right idea though. We had the right idea that it was going to act like 1 over n squared. So that allows us to use what tests instead? What would we use instead? Yeah, so we could use like either the direct comparison test or the limit comparison test. Yeah, there has to be a singular term on the bottom, n to a power, or n to a power times log of n to a power right here. What if the ln has a power other than 1? Well, that's what this q is here for. So if we have ln of n squared and p was equal to 1, then we would take a look at that power right there. But yeah, how do we deal with things like this? We're going to use the direct and limit comparison tests. So direct or limit comparison tests. And remember, the condition for these is that your an needs to be greater than or equal to 0 here. All right, is the limit comparison test better than the direct comparison test? I certainly prefer the limit comparison test because then I don't need to worry about which way the inequalities are going. So I don't have to bank on the fact that, oh, all of these are pluses here, so that's going to work out in my favor. I could just go ahead and use the limit comparison test and not worry about that at all. So are we being able to pick which test to use? Yeah, in most cases, yes. You might just be asked like, oh, does this series converge or diverge? And then you might have to say, all right, which test did you use? There could be things like that. So yeah, you're welcome to use any test that you like. Are there instances where the DCT will work and the LCT won't? Yeah, so for something like, let's say we have the sum of sine of n over n squared, it would be easier to use the direct comparison test here. Let me actually modify this. Yeah, there we go. It would be easier to use the direct. Wait a minute, I'm getting this all backwards. See, I don't like to use the direct comparison test because it's easy to get the inequalities turned around. And this would have to be an absolute value to make it positive. Yeah, okay, this one I would use the direct comparison test on because absolute value of sine of n over n squared is less than or equal to 1 over n squared. And we know this converges by the p-test. So this would be an easy one to use the direct comparison test here. What lecture did we learn this in? We learned this, yeah, we had a whole lecture on the limit and direct comparison test too. I forgot what number they were though. 19 and 20, thank you very much. All right, so yeah, so the direct and limit comparison test, to summarize them, they work for things that kind of look like an easier test. So this kind of looks like we should be able to use the p-test on this, but we can't quite do it. So we compare to easier series. That's kind of the whole point of these comparison tests here. But would the limit comparison test not work? It wouldn't work if we picked 1 over n squared. It would work if we picked a different n, like 1 over n to the 3 halves or something like that. But that's a little bit more complicated. So in this case, you could use limit comparison, but it would be harder to do that. How would you normally determine what to compare it to? Usually if you have something over something else, like let's say we have like 3 to the n plus n squared and 5 to the n minus n cubed or something, you're going to pick the more powerful terms on the top and bottom. So the exponential terms dominate here in this series. So I would probably compare this to 3 to the n over 5 to the n. That would be what I would end up doing here. That's right, yeah. So if we wanted to analyze this further, we could say that this is 3/5 to the n. And yes, that will converge by the geometric series test. So then we would do probably a limit comparison. I don't know. I just do limit comparison, so I don't have to worry about the inequalities and get those flipped around. And then we would do that limit, and we would probably get 1, and then we would end up getting something that converges. How would you do series with sines, cosines, and tangents on the top here? Well, actually, so one thing that has to do with the limit comparison test specifically are these. Remember that if we're doing comparisons, we say that sine of 1 over n to a power, we could replace that with 1 over n to a power for purposes of doing the limit comparison test here. With cosine of 1 over n to a power, it doesn't matter what power that is, we just replace it with a 1. And with tangent of 1 over n to a power, when we're doing limit comparison, we can replace that with 1 over n to the p right here. All right. So for example, if we have something like sine of 1 over n divided by n right here, then we could do a limit comparison to 1 over n divided by n, which would be 1 over n squared. So that would give us the clue that this series is probably going to converge right here. All right, so someone asked a question, oh, can you have a constant for Bn? I suppose you could, but if you have a constant for Bn, like let's say Bn is 1, the series for 1 will diverge. So if you're doing a limit comparison with something to a constant, that thing is probably going to end up diverging. That doesn't really happen very often, though. Usually we don't compare them to constants here. All right. Anyways, so that's the limit comparison test. What else we got here? A few more tests. We have the alternating series test. The alternating series test says that if we have an alternator times something else where this thing is greater than or equal to 0 right here, then if an is decreasing and going to 0, then the series converges. All right, so if you ever see an alternator on any kind of series and you need to know if it converges or not, the alternating series test is an excellent place to start because this is probably one of the easiest tests to use. You just have to see if your an is going to be decreasing, and then you need to see if it's going to 0 here. Please don't put a really hard alternator on us. Well, yeah, let's go over some of the other alternators so you guys will be ready if I decide to be mean and do that. So -1 to the n, obviously, is our kind of basic one. But these are also okay. So all of those are okay. There are some with trig functions. Cosine of pi n and sine of pi n plus pi over 2. Those are okay. But some things that aren't okay are just sine of n. That's not going to work. Cosine of n, that will not work. If we flip the inside of these, like sine of pi n, that's not going to work. So for example, actually, we know what this one is. What's sine of pi times n? Does anyone know what that is? It's 0, right? Sine of any multiple of pi is going to be 0. So that definitely can't be an alternator here. And finally, another one that you don't see too often, but I guess I'll just say it anyways. -1 to an odd number times n, that's okay. So like -1 to the 3n, -1 to the 5n, those are all alternators there. Just for, you can tell if a series diverges through the alternating series test. That's right. So kind of like how with the the test for divergence, we couldn't tell if something converged. Notice that we only can tell convergence from the alternating series test. If you take the limit of this and it's not 0, then I would strongly consider using the test for divergence on that. So the test for divergence you could think of as kind of like an opposite to the alternating series test right here. All right, so that's alternating series. Let's see, we have 2 more tests. We have the root test. And the root test is nice because there are no conditions on what AN you could use it on. With the root test, we just look at the limit as n goes to infinity of the absolute value of AN raised to the 1 over n power right here. And depending on what this limit is, so there are 3 options. So this is L. If L is between 0 and 1, we converge. And we converge absolutely if that's a distinction we care about. If L is greater than 1, we're going to diverge. And if L equals 1, then the root test is inconclusive and we need to use a different test instead. All right, so there's the root test, and it works very good, of course, whenever we have something with nth powers. So if you have nth powers, then the root test is something that you're going to probably want to use here. All right. Well, we have to determine whether a series converges absolutely or conditionally. Yeah, that is entirely possible. You may have to do that. And then the ratio test is our last and most useful test. So there are no conditions on that one either. But the limit is different than the root test. We have the limit as n goes to infinity of the absolute value of AN plus 1 over AN right here. And that's going to be the limit that we're going to think here. We're going to compute here. And then the same conditions apply that we had for the root test. So the reason why the ratio test works is we're seeing about the relative size of the future terms as compared to the past terms. So if this fraction is bigger than 1, that means that the terms that are coming up are going to be bigger than the terms we already had. So this is kind of getting bigger and bigger and bigger right here. Oh yeah, so there's the series flowchart. So I was going to post that later today. So I made a flowchart for series. I don't know. I kind of have mixed feelings about advertising that because you're not allowed to use that on the exam. So I wouldn't become too reliant on that. But when you're first starting out with series and you want some help, that flowchart is good. Is that the one that we had last semester? Let's see. Where's the folder on this? We can memorize it and write it first thing. I guess you could do that. I don't know if that's a good idea or not. But yeah, anyways, if that's not the same chart, I'll post the one that I have later, which probably is this one right here. But yeah, there's kind of a flow chart, like kind of gives an algorithm. Not every series fits into the algorithm, but most will. So that kind of gives you a place to start there. Let's see here. So we have some questions. Actually, so I want to say probably the best way to study for this test is to kind of do something similar to what I did for lesson 23. So if you watch lesson 23 on YouTube, that was the one that we missed. I essentially just went through a ton of different series and just thought about each of them and like whether they were going to converge or diverge. That should be most of what you're doing for your studies. The more you practice those and the more you go through those, the easier it'll be when you encounter series in the wild, like on the exam. And then I would spend probably the rest of the time maybe going over some of the specific things like, you need to be positive, decreasing, continuous for the integral test. I would maybe go over some of that as well. Any websites have a bunch of practice problems like that? Oh, I guarantee it. Also, if you look at the online textbook that we have, there are a lot of practice problems in there. So there's a link to an online textbook on the front of Canvas that has a ton of series that you can look up there. When am I going to put the flowchart up again? I'll do it later this evening. All right, but anyways, that's all of our different tests here. So I kind of wanted to reacquaint you guys with all 10. I think there are 10. Yeah, all 10 of those, and the difference between sequences and series. Now we kind of have our main characters introduced here. So, or should we study the max error? Yeah, so that's something you need to know as well. So for the alternating series test, thanks for reminding me of that. Remember that there was a way of determining the error when you use the partial sum instead of the series. So the error for Sn minus the series is going to be less than an plus 1. So if you only want to add up to the nth term rather than adding up all infinitely many terms, there will be some error, but the error won't be any more than the next term you would have added right there. Oh, thanks for reminding us of that, Christian, as well. So back with the limit comparison test, another thing that would be good to remember is what E is. So the limit as n goes to infinity of 1 plus a over n plus b to the n is e to the a. That's definitely a useful limit that I would know about. Is this test being graded out of 105 again? Yes, it is. Can we do arctrig functions? Yeah, we'll see things that have like arctan and arcsine, I guess. Okay, so I think a lot of people are just asking general questions now. So let's go ahead and get started with that. So I'm going to try to do the same thing that I did for the previous review. So I'll take 3 questions from you guys on the chat, and then I'll take a question from the people in the audience here. All right, so yeah, so go ahead and put in your questions, but please don't put it in more than one thing here because that'd be cheating. So go ahead and ask some questions here. Oh yeah, sorry, the denominator of the E thing is n plus b. Partial sums, practice exam 2, 3. But be sure to specify which thing you mean. Practice exam, absolute, conditional. Let's see. Kind of seems like practice exam 6 has a lead here. Let's take a look at that one. Oh yeah, and this one actually overlaps with some other people's questions here too. So yeah, let's take a look at that. All right. Practice exam 6. So this was the sum from n equals 0 to infinity of arctan of n plus 1 minus 2 arctangent of n plus arctan of n minus 1. All right, so let's go ahead and see what's going on with this. So we in this one they asked us to find the sum of the series or state it diverges. Okay, now if they're asking us to find the sum of the series, that means it can only be one of 2 things. It's either going to be telescoping or it's going to be geometric. And which one is this going to be? Yeah, this one's pretty clearly telescoping. We don't have anything raised to the nth power here. That's right. So this is going to be a telescoping series. Why is it telescoping? Well, there's 2 reasons why it could be telescoping. They asked us to find the sum of the series, and this is definitely not a geometric series. Geometric series is where we have something to the nth power. So this has got to be telescoping then. Another reason why we could recognize that it's telescoping is because we have a bunch of similar functions, right? We have a bunch of arctans with the only difference between them being that we're shifted by a bit in each parenthesis here. So here we're shifted up by 1, here we just have an n, and then here we have n minus 1. So that's another kind of sign for telescoping series here. Yeah, in terms subtracted from one another. That's right. So similar looking terms that are subtracted from one another. That's an excellent sign of it being a telescoping series. All right, now what do? Well, we start writing out the terms until we see a pattern. So let's write out n equals 0. It's arctan of 1 minus 2 arctan of 0 plus arctan of negative 1. All right, let's do n equals 1. We have arctan of 2 minus 2 arctan of 1 plus arctan of 0. All right, let's do one more here, and then I think we might start seeing some interesting things happen. All right. Arctan of 1. All right, and then now I think we could start to see some pretty significant cancellation here. So I have arctan of 1, negative 2 arctan of 1, and then another positive arctan of 1. So those will all cancel out with one another. If I move on to the next one here, plus arctan of 2. So we have arctan of 2, and then negative 2 arctan of 2. Like that. Can we split it up into two different telescoping series? I would watch out for that because of divergence issues. Like they might both be divergent, but then together they would converge. So I wouldn't recommend doing that. Plus, that would actually take more work to do. So I wouldn't recommend going that way. All right, so let's do one more just for emphasis here. Arctan of 5 minus 2 arctan of 4 plus arctan of 3. And we see that the arctan of 3s will then cancel out. So it seems pretty clear that the pattern here is that we're always going to have this stuff up here. So there's never going to be another arctan of negative 1, another arctan of 0 for us to cancel with. And then it seems like we always have this bottom triangle of things that keeps getting bigger and bigger and bigger. All right, so with that in mind, let's write down our formula for our partial sum. So our formula for our partial sum will definitely have these three up here. Negative 1 and an arctan of 0, and we'll simplify that in a minute. Now, let's try to figure out the pattern with the remaining terms here. So when we decided to stop at n equals 4, we had an arctan of 4, an arctan of 5, and minus 2 arctan of 4. Now, these we can combine into a single negative arctan of 4. So it looks like we have minus arctan of the current number, which was 4, and then we added in an arctan of the next larger number, which is going to be 5 here. All right, so this is our formula for partial sums right here. Now, let me ask you guys this. What's arctangent of 0 equal to? Does anyone know what that is? What angle do you put into tangent to give you 0? It's going to be 0. That's right. So this is a big old 0. That means this is a 0 as well. Arctan of negative 1. So what angle do we put into arctangent? Or sorry, what angle do we put into tangent to give us negative 1? Something in the fourth quadrant. Negative pi over 4. That's right. So this is just going to turn into negative pi over 4. All right. And remember, arctangent values are always between negative pi over 2 and pi over 2. So we couldn't say negative 7 pi over 4 for that, even though that would also make tangent be negative 1. All right, so this is our sequence of partial sums. Now remember what a series is. The series is literally the limit as n goes to infinity of our partial sum. So we kind of repeat this process forever. That's what this limit is saying. We keep doing this process forever and ever and ever. So we're doing the limit as n goes to infinity of this and then we'll see what's going to happen. So what's the limit as n goes to infinity of arctan of n? Does anyone remember what that's going to be? It's going to be pi over 2. That's right. That means this is going to pi over 2, and the plus 1 doesn't matter if n's going to infinity. This is going to pi over 2. So we have minus pi over 2 plus pi over 2. So when those cancel out, we just end up with negative pi over 4. So that's what this series is going to end up converging to here. Let's see. So I think I've had a few questions about where I got these from, these two terms. I like to kind of figure these terms out by looking at the last row that I wrote down once I saw the pattern. So my last number that I wrote down was 4, right? So we have arctan of 4 here, so that's the same number. We have another arctan of 4 here, that's also the same number. And then we have arctan of 5 here, that's one number bigger. So I have plus an arctan of n plus 1, one number bigger. That's where this came from. And then these were actually the same, so I can combine them. So this is one of these minus 2 of them gives me negative 1 of the current number that I'm at. So I have minus arctan of n right here. So that's where I got this from. So you kind of have to pick what number you stopped at and use that to help you set up the remainder of this over here. All right, so that was a good question. All right, it's time to spam your questions again. Okay, so we say that arctan of n plus 1 approaches arctan of n. Well, yeah, that does end up happening. I mean, they don't cancel out before you do the limit. Once we do the limit, then we can cancel them out. All right, let's see. Remember, don't spam it more than once. I see some people doing it multiple times. All right. So based on this, let's go ahead and do problem 11 from the practice exam here. You mean once I do the limit? Yeah, so after the limit, they end up being the same thing. You can't cancel them before the limit. So you need to do the limit in order to do what you're saying. All right, anyways, sorry, I got distracted for a second. All right, let's do practice exam 11 here. Okay, so use the limit comparison test to determine if n equals 2 to infinity of 1 over sine squared of n and ln of n converges. And this is a multiple choice question. So they kind of gave us a few different options here. So let's go through some of these options and see if which ones are going to be true or not. Okay, so the first option I have on my screen is use Bn is 1 over n ln of n, and the limit does not exist, so the series diverges. Okay, now we actually don't even need to do a limit to see why this one is wrong. So if the limit you get out of the limit comparison test doesn't exist at all, it's not on the spectrum from 0 to infinity, right? And that was how we judge whether or not the limit comparison test gave us something useful. So if it just doesn't exist, then it's not going to say anything. It's not going to say whether it converges or diverges at all. So that's not going to be correct for sure right here. So let me explain that again. So with the limit comparison test, we need a limit between 0 and infinity. And does not exist is not a number, so it's not going to be between 0 and infinity. So if we don't get something in between 0 and infinity, we can't conclude anything from the limit comparison test, neither convergence nor divergence. All right, so that one's not going to be right. Let's take a look at our next option here, at least on my computer. I have it shuffle of the answer choices. Use Bn as 1 over n ln of n, and that yields 1. So the series converges. All right, now let's think about this. Let's think about what Bn does. So Bn as a series is the sum of 1 over n ln of n, right? Is this going to converge or diverge as a series? This is going to diverge, right? And this is going to diverge by the generalized p-test, because we have 1 over n to the first power, and we have ln of n to the first power as well. So this is going to diverge by the generalized p-test. Now, when we do limit comparison test or any comparison test, we want our series to do the same thing as our comparison. So we can't say that our series converges here if our comparison is divergent. So that definitely doesn't make any sense. So that's not going to be correct either here. You don't have to make your Bn anything in particular. You can make your Bn be whatever you want. It's usually just recommended that you pick the dominant term on the top and bottom. Okay, let's look at our third answer here. So this one, use the limit comparison test, and this time they have a different Bn. It's 1 over n, ln of n, and then ln of n. All right. And then they say that this yields infinity, so the series diverges. Okay, well, this part at least makes sense. If we get an infinite limit from the limit comparison test, then we're going to get divergence so long as this diverges. So let's think about this. Is our comparison series, is this going to converge or diverge? What do you guys think about that? Yeah, this one's going to diverge as well. And why is that? Well, we have 1 over n to the first power. Okay, that means we look at the power of log, but the power of log will also be 1. So if we happen to have a log of a log there, that's kind of the next step, and then we look at that power. But that power too is also going to be 1. So if all of the powers of all of these things are 1, then this is going to diverge by, I guess you could say maybe, I don't know, like a super generalized p-test. But the same reasoning applies as you nest more and more logs together. You kind of just go through the powers until you get to one that isn't 1. But if they're all 1, it's going to diverge. Yeah, the generalized p-test, so we first look at the power of n. If that's bigger than 0, or sorry, bigger than 1, it's going to converge. If we have this being less than 1, then it's going to diverge. But if it's equal to 1, then we look at the power of log and do the same thing. So if this is bigger than 1, we converge. If it's less than 1, we diverge. If it's equal to 1, then if we have a term like this, log of log, we look at that. And if this is bigger than 1, we converge. If this is smaller than 1, we diverge. But once we've run out of these, if it's equal to 1 and they're all equal to 1, then it's going to diverge here. All right, so this diverges. So let's actually do the limit comparison test here. So we have 1 over sine squared of n ln of n. So that was our an. And then we divide by bn. So I'm going to put the reciprocal of it here. All right, so let's see what happens with this limit. Well, the n's will cancel, the logs will cancel. So we end up just doing this, the limit of ln of n divided by sine squared of n. All right, now the thing is that what's the top doing? The top is getting bigger and bigger and bigger, albeit very slowly. Logs already grow slowly. If you have another log plug in there, it's going to grow even more slowly. But this is still going to go to infinity though. Whereas the bottom, it's oscillating between 0 and 1, right? So if you take a larger and larger number and divide it by something bouncing between 0 to 1, what is going to happen? What's the whole thing going to do? It's going to go to infinity here. So the top's already getting really big, and we might be dividing by a tiny number, so it's only going to get even bigger here. So we end up getting infinity from this, and since this diverged, then the original series will diverge as well. So this one actually ended up being the true one here. So if we get infinity and we want to show divergence, that's okay. And if we get 0 and we want to show convergence, that's okay too. But usually we want to try to get something in between 0 and infinity. Oh, do you have a question? No, the statement was using this comparison yields infinity, so the series diverges. Okay. Yeah, you use it to determine if the series converges. That's like yes or no. And would you, like, if for whatever reason this is like a big response question, do you expect to go create this B so then? Yeah, if it were something like that, then yes. But this one's, I remember I like to make the practice exam harder than the real one. But yeah, you do have to come up with your own BN in general. All right. If the bottom would have been cosine squared, would have been the same. That's right, because that also oscillates between 0 and infinity here. All right, so 1 over n ln of n squared. If the square is on the natural log, that will converge. Why can't we use 1 over n ln of n as our bn? Because what will happen is, if we only have this as our bn, then these will just cancel that, and then we just have 1 over sine squared of n, and that won't convert, that won't go off to infinity. That's just going to keep oscillating around. So that one's not going to exist. That's right. Yeah. So that so the comment was, so that's why we have the ln of n here. That's right. We have this, so we have something on the top still going to infinity here. So that's what inspired me to have this extra term in here. All right. So let's see here. I have time maybe for like one more quick question here. But don't worry if you weren't able to ask your question, we still have on Friday to go over questions as well. So does anyone have like a really quick question, maybe like kind of like a conceptual question or something like that, maybe like a quick.
Professor Manley, do we need to worry about bigger or smaller things for limit comparison tests? Like, do we need to worry about BN being like bigger or smaller?
No, so that's the whole point of limit comparison test, is that you don't need to worry about that. So you don't need to worry about whether something is actually bigger or actually smaller. It really just matters what the limit of them is doing. All right, practice exam 20. That's actually a pretty quick question here. Let me share my screen to this real quick. Let me share my screen to the practice exam. All right, can people in the chat see that? Can you see practice exam 20? Okay, good. All right, and then people in here can see it. All right, so which of the following tests can be used to show absolute convergence? Select all that apply. Okay, well, first of all, in the root and ratio test, it says that if it converges absolutely. So we know we can pick these two for sure. The direct comparison test and the limit comparison test, what's the requirement for that? We can only use those on what types of series? We can only use those on positive series, right? So if a positive series converges, then is it going to converge absolutely? Yeah, it is, because if we put absolute values on there, it's not going to do anything because it already was positive. So since these had to do with positive series already, if they show that they converge, well, then you know they converge absolutely too, because putting an absolute value on these series won't do anything. So it'll also show absolute convergence here. All right, the alternating series test. Well, the alternating series test shows that something converges, but you need an alternator for that to work. What would happen if you put your absolute value there? Then your alternator wouldn't go away. So you can't use the alternating series test to show if something converges absolutely. And then the test for divergence, is this one going to show absolute convergence or no? Yeah, this one is not going to show absolute convergence because it can't show any type of convergence because it's the test for divergence. So it's going to be these four right here. So it's going to be these four. All right. Yeah, so let's recap this real quick and then we got to go. So the first two right here, it works because it's literally in the definition of the test that those converge absolutely. And then the second two, the direct comparison and the limit comparison, those only work on positive series. And if those converge, then they converge absolutely too, because putting an absolute value on there won't change anything about them. So it's going to be the top four on this list. Why is it not alternating? Because if you put an absolute value on an alternating series, it'll get rid of the alternator. So you can't even use the test anymore. All right, guys, that's all we have time for here. So I will see you guys on Friday when we will do some more review. So have a good week.